In this chapter, I introduce the concept that you can conceptualize, you can think about the matrix inverse as a least squares problem. So you can think about your matrix inverse as being like a matrix of beta values that gets you from a square matrix, which you think of as a design matrix, onto a data matrix, which is the identity matrix. Now, this is not super useful for like practical computations in the sense that in practice, you don't really want to compute the matrix inverse using methods to solve least squares, and certainly not the left inverse, which I'll talk about in a moment. But conceptually, I think this is a really nice way to form links across different concepts that you are learning about in linear algebra. Okay, so with that in mind, that is really the goal of exercise 5 here, to implement this. So consider the equation xb equals y. So x is a matrix. We're thinking about it as a design matrix, but actually it's a square full rank matrix that you want to invert. Y is a matrix that we kind of think about as being observed data, but actually it is the identity matrix. And B is a matrix of beta coefficients, kind of like beta coefficients that will map X onto Y, so the design matrix onto the observed data. But instead of being really like beta coefficients, like regression coefficients, they're actually going to be the columns of the matrix inverse. So I hope you found this a useful discussion when I introduced this concept earlier in the book chapter. Okay, so now what I want you to do is compute this matrix B in 3 ways. First, using the left inverse least squares method, and this you do in a for loop to compute y one column at a time. Now, if you're a little bit confused about how to approach that, then please consult earlier in the chapter where I go through this in more detail. Okay, and then use the left inverse method to compute the entire B matrix all at once. So using matrix operations without using a for loop, like in the first method. And then third, you want to compute the explicit inverse using numpy.linalg.inv. And then you multiply x times b for those 3 different b's, those 3 different methods of computing this matrix B. And then, just visualize them and you should see that they are all the identity matrix. And then you can compare these 3 different solutions to see if they are similar to each other. Okay, now I have a longer discussion here about that. It's strange to say the least to use the inverse x transpose x to compute the inverse of x. It's really circular. I mean, it's redundant. We're just computing the inverse to find the inverse. Basically, it doesn't make much sense computationally. But again, the purpose of this exercise is more conceptual. I want you to understand the concept, the idea that least squares can be used to interpret the matrix inverse. Okay, so now I will switch to Python and I'll show you my code solution. So here I'm creating a design matrix. It's a random 6 by 6 random numbers matrix. But in the context of least squares, we are thinking about this as a design matrix. Similarly, this is the target matrix. You can think of this as like the data. These are like the observed data. But in practice, this is just the identity matrix. And what we want to solve for is the matrix of coefficients that will transform x into y. So it'll give us predicted values, which are actually the identity matrix. And of course, that matrix of unknown coefficients is the inverse of x. Okay, so here I show method 1. Here I'm looping over the columns, and I populate the inverse of this matrix, which in the text that I just showed, I called this matrix B. Here I'm calling it xinv, because that's really what it is. It's the inverse. And then, here's this kind of funny thing where I'm using the left inverse of the matrix to get the inverse of the matrix. But again, I want you to see the concept of relating these different ideas that I've been presenting throughout the book. Okay, here it turns out, we don't need to solve this in a for loop going column-wise. We can do the whole thing at once using matrix multiplication. And then here is just the explicit inverse function. Okay, and then here I plot all three of these. And then here I'm just showing that they are equivalent. So here we expect these to be zeros. These two are exactly zero. So whether we use the least squares method column-wise or matrix-wise, that ends up being all zeros. And then here you see, yeah, these are, near zero rounding errors. Sometimes we see rounding errors smaller than this, like 10 to the minus 15 or minus 16. Here, these are around 10 to the minus 14 to minus 15. So, when you have a small random numbers matrix like this, which is relatively numerically stable and well-behaved, it has a well-behaved inverse that is relatively easy to calculate. And so we don't really expect that many numerical errors here. This would, this method is suboptimal when you are working with larger matrices or matrices that might be harder to explicitly invert.